Hello, everyone. My name is Chopin Shen. I am an associate professor at Penn State University. I work a lot with deep learning in water resources. And now there's a growing interest in deep learning across various different scientific domains. And many people are asking me, how do I get started? So I would say, before we start to dive in all these architecture about this network and that network, I think it's important to understand the basic mathematical core. What is backpropagation? What is gradient descent? And this is what we're trying to explore in this video using a very simple example. Okay, so we're going to do linear regression with a very simple hydrologic example. This is the area that I'm familiar with, although the data set is just a data set. It could be anything. Okay? What is the loss function? How do we minimize it using gradient descent? And how do we implement the code? Okay, all right, let's get into it. So what is regression? The regression estimates the relationship between a dependent variable, what we often call the outcome variable or target, and one or more independent variables, and which we often call as predictors, covariates, or features. Okay, so in the simplest case, you have only one predictor variable and one target variable, and we can build a simple relationship. So if you're doing linear regression, it's essentially what we've seen before is drawing a line that goes right through the dots, right? That has the smallest distance from all the data points. Here, I would talk about a rainfall runoff example where the dependent variable is called long-term average runoff, okay? And the independent variable is the long-term average precipitation. Okay, so this is a hydrologic example, but you can understand it as any other data set in the world that has one dependent variable and one independent variable. Okay, so we know that in a basin, after it rains, water is going to rush out as runoff. So we record it every year. We record how much runoff there is, how much average precipitation there is, and we average it across the year. So on this data set, every little data point here you see is a basin. Okay, is a basin. And the x-axis is the long-term average precipitation, the y-axis is the long-term average runoff for that basin. And the relationship that we want to learn here is annual mean runoff is equal to a linear coefficient W times the annual mean precipitation plus a bias term. Okay, now you can fit this using very simple relationships, very simple libraries such as sklearn, right? You can call a linear model, you can fit it. It's just one statement, very simple, but that's not the point here today. The point here today is I want to show you how we solve the problem using gradient descent, because this linear model is essentially a prototypical model that if you understand, you can apply the same concept to much, much more complex models. Okay. All right, so here's some code where I showed how we do some data wrangling, where you read off the CSV data set. Let me show you what the data set actually looks like. So if you read it, it's essentially a spreadsheet. Okay, it has years on the y-axis and the gauge the different basins on the columns. Okay, so for every column you have different runoff values in millimeters per year for different years. So we first do a little bit data wrangling. We read this data into a pandas data frame, and then we average across the time dimension. So we get one long-term average runoff per basin. Okay, so after you do that, now we have 600, I believe 671 basins, right? So you have 671 data points. Now we do the same thing for precipitation, which is another spreadsheet. Okay, another spreadsheet that has precipitation rather than runoff being tabulated, and we do the same aggregation along the time distance. So every basin has just one precipitation and runoff. Okay, so let's get into a little bit of math. And I use this math so you see what the machine learning platforms are actually doing under the hood. Okay, so that's why we need a little bit of math here. To write it as a mathematical formula more concisely, we know that y is equal to some bias term times the linear terms, and you can write it as a concise inner product between the w and the x, right? However, normally we have n data points in the sample. For example, in this case, we have 671 bases, right? So that n would be 671. You have these data points at that same line needs to go through all the data points, right? So this is repeated for n times. You have n set of predictors and n outcomes, right? So this concisely can be written into a matrix product, a matrix multiplication, which is the weights times the x. What is the x? The x, you have a 1 as the first row, okay? And that is the x, you think of there's a b and a 1 multiplied with w0. And the first is the first predictor. You can have d predictors. Okay, that would be a d-dimensional problem. However, here in this problem, the d is 1, so you would only have those first two rows. If you transpose it, xt becomes 1, 1, 1, and xx. And this is the first predictor, okay? The second predictor, and the number of rows is the number of data points, okay? The w is w0, w1, w2. Of course, if you write it as wx times b, the w0 is actually the b term. Okay, so now I just want to write it as a matrix multiplication term so you can see more clearly what happens next. All right, so in general, this model can be understood as a hypothesis. Okay, this model is a hypothesis with some parameter w. Okay, some parameter w. And with input x, okay? What we're trying to do here is to minimize certain objective, okay? We call what we call a loss function for sample s, okay, for sample s. The loss function indicates how far the model is from the observations, okay? We seek to minimize this loss function by tuning the parameters in the model. Okay, so in this case, that would be the weights on this model H, okay, for the sample data S. And when you solve argmean, you get the W, the optimum W out of this argmean operator. Okay, so for brevity, a lot of times we ignore the sample. We call it L instead of LS. Okay, a very common loss function. Now, there's more than one loss function, but a very common one would be mean squared loss. Okay, mean squared loss. In this case, you have H, the model prediction, minus Y star, which is the observed value, and you take a square, and you sum up all the data points. You take the mean of it. Okay, so imagine you are fitting a line. Okay, this is your model. And these are the data points, and that model, because of its inherent simplicity, is not going to fit all the data points, right? Not going to fit them exactly. So there's going to be some distance, and that distance is characterized by this error term, okay? Could be positive or negative, but when you square it, they all become negative, positive, and you sum up the squares, you divide it by n, that's the mean squared loss. Okay, so for linear regression, we want to minimize this distance. We minimize the distance of that line from this data points. And graphically, you could imagine the only way to minimize this is to put the points right through the middle across these data points. We have multi-dimensional cases, in which case maybe you have two predictors. This becomes placing a plane across the 3D data points. And it could be much higher dimensional, okay? So here I show you that if you are not going across it, if you overshoot the slope, then your distance will be very large. Okay? So how do we solve this problem? So we normally solve this problem using, we can solve it analytically you can solve it so that the derivative, okay, the gradient of the loss function is equal to 0. That's where you get the extrema for the loss function, right? So calculus 101. And here we want to take the extrema so that we find the minimum, right? And you can solve a matrix, blah, 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 but I'm not going to go through that here, okay? That's not the point of this presentation. You can go and look at calculus or elementary statistics textbooks. I want to talk about gradient descent. And for gradient descent, we want to understand this concept of a loss landscape. Okay, the loss landscape, thinking about a landscape where you have a plane where you have two parameters that serves as the axis, and the loss function is the z-axis. Okay, so you see in the example that's demonstrated here, you can have a kind of a contour that demonstrate how does this function behave. Okay, this is what we call the landscape. So if we try to guess different slopes across this data points, we will find that the loss is pretty high, right? The loss is pretty high. If you change it, this is where you use a flat line to approximate the data points. It's actually not the worst, right? You can do a lot worse than that, but it's still nowhere close to the minimum where we want to be. Okay. All right. If you further tilt that slope now closer to the data points, you'll find that it's closer to that minimum, right? So it's getting better. It's getting towards that minimum. Okay. If you're in 3D, this looks like this. You want to guide your algorithm. Maybe you're starting from somewhere here. You want to guide your algorithm toward that minimum. So this is how we want to optimize this function. Okay, so moving beyond solving that closed form analytical solution, we want to introduce a very important way of solving minimization problems for high dimensional parameter sets. This is called the gradient descent. Okay, the reason we want to do this is that you might have very high dimensional problems where analytical solution is unattainable, okay, or very inefficient, or you might have nonlinear equations that are difficult to solve analytical solutions for, and the matrix may not be invertible. Okay, and this linear regression here serves as a prototypical problem where once you understand how these core methods work, you can apply to more complex models. Okay, for most problems other than linear regression, the direct immersion is not applicable. Okay, so this method of gradient descent means that we climb down the mountain little by little, following the steepest slope. Okay, as you would imagine, the steepest slope is indicated by the gradient in that loss function. So we will just have to climb it down little by little. So every time we climb, so for example, here, I know that my slope points this way. Okay, so I just want to go down a little bit. Why don't I want to go down a lot? We'll explain this later because it's a highly complex landscape. If you take it too big of a slope, you might overshoot. Okay, so this is the method of gradient descent. We want to calculate the gradient of the loss function with respect to the parameters, and then go down along that slope. So this is implemented by a simple calculation when the k plus 1, when the k is the kth iteration, kth guess of your parameter sets. You take it and you subtract alpha times the gradient. Okay, in a multi-dimensional case, this is the k plus 1 is the newer guess. Okay, it's the newer guess. So it's graphically equivalent to knowing this slope and then take a walk along that slope down. Okay, for one parameters, this is wj minus alpha del L over del that parameter wj. Okay, as we see immediately, this method, there seems to be no difference between these different dimensions, right? They all take the same learning rate, and this is why we need some pre-processing to scale the features. Right? It's very clear. If imagine your W actually have a dimension, so you can take. It's also very obvious from here. that you have a ellipsoid shape in that landscape. So you can't take an equal amount of walk in both directions. Okay, that would not be an efficient search. What I mean is, if you're here, let's say you're here, you can't take a walk equally in y and equal in x. You should preferably go down more in this direction and go down less in this direction. Okay, but the gradient descent method doesn't actually account for that. So there's some data processing that's needed for that. Okay. All right, so let's dive in a little bit more to the gradient descent method for linear regression. Okay, we apply the gradient descent. The L, okay, is the sum of squares of the error. The Y is the prediction here, and Y star is the observation. So if we applying chain rules, if we are interested in the gradient of L with respect to any parameter Wj, okay, using chain rules, we'll know that the first layer is to do the differentiation against this yi here, which you then get, it's yi minus yi star times the yi, that's the prediction, okay, that's your model, with respect to wj, okay? So this is chain rule, essentially. It's applicable whether the wi has relationship with with yi has the relationship with wj or not, whether the relationship exists or not. This function exists. This formula is correct. Notice this is simply the error. This is simply the error, the distance. So we can simplify it as ei here, multiplied by this gradient of the model with respect to that frame. Okay. Now further introducing the model, which is the gradient descent, okay, which is the linear regression. Is the x times w, is a simple matrix multiplication. Okay, for the ith data points, okay, we apply the same formula, we substitute it in here, we get this one, and you realize that, okay, this is still ei, right? That's still the error. This term is still the error, but this term, it's simply a multiplication, right? And that multiplication with respect to wj is simply xij. Okay, the j would represent the jth dimension. Okay, recall that in our previous model, the x0 is 1, right? x1 is, so x0 is 1. x1 is the first predictor. Okay, so this gradient of L, this derivative with respect to the parameters is 2 over n, the error times the errors times a multiplication with 1, 1, 1, 1, 1, and x the first predictor, okay? And if we only have two parameters, y is equal to w0 times, here think of there's a 1 here, plus w1x, we have a 1 by 2 vector, right? So this is, you have only two vector, two elements, two parameters, so 1 by 2 vector. And that is E1 times E2 plus En. Notice that you have n, a vector of n size here, okay? And here you have then a n by 2 matrix, which is you have n1 here and x1, x12, x1n, okay? So because there's only one x, but n data points, right? And you put it together, that's 2 over n, the summation of ei, and the summation of ei times x. So those are the two gradients that theoretically we should find and use in our gradient descent. Okay, so this is the formula, and again, this is how we take a walk along the steepest slope down. And in the code, this is often written as grad vic is equal to mean of the error, okay? The error times the x, okay, here. Notice notice this error, okay? But the error times x, so the x is 0, x knob here is 1, right? So that's still fit. And then we update the gradient vector using the WVEC is equal to WVEC minus the learning rate, which is this alpha times the graph rate. So this is how you implement it. All right. Notice that I just mentioned that your data might have its own dimensions, right? Might have its own units, and walking in those directions might not mean the same thing, okay? And that's where the steepest slope may not be the slope you want to take. So kind of to avoid that problem, normally for machine learning algorithms, we do something called scaling, okay? Scaling, one way to do scaling is normalization. And I do this by subtracting the mean of precipitation divided by the standard deviation, okay? They essentially get a z-score out of this. So this precipit 1 is a z-score. I similarly do the same thing for runoff. Okay, you want to do this for both the predictors and the target. Okay. And this is in the code how I do it. You can do it in other ways. Okay? You can subtract the minimum and divide by the max. The maximum of the value, subtracting the minimum of the value. Okay, that is called a standardization. And both schemes have been used in machine learning algorithms.